That's a lot of money laying around. We can talk about that. This is one of the things that had no name. It is the 60-inch telescope. And we call it that because the primary mirror that runs along the bottom of the telescope here is 60 inches, or for those of you who can do multiplication, 5 feet across. The piece of glass in this telescope is about 6 inches thick, a little thicker, I think, and weighs around 1,900 pounds. And it was, when it was made, in about 1896, 1894, I think. It's the largest single piece of glass existing in the world for any reason. So, George Ellery Hale, I talked about him in the guy who founded the observatory, was very interested in studying stars. He knew that to study the sun as a star, he didn't know about other stars, not just the sun. So he decided to build nighttime telescopes. This telescope is like no other telescope that existed before. It is a unique engineering phenomenon. Other people had tried to make telescopes this big, but the primary problem they had was that they were impatient, they wanted to make it quick, and they just didn't have enough money to do it right. So here at Mount Wilson, we had zillions of dollars from the richest man in the world. Money was not a critical issue, but actually it was, because everybody went over the budget, but it wasn't as critical an issue. And we had people who understood that patience is a virtue, especially when you're trying to do something nobody has ever done before, which is make a telescope this big that works. Other people had to make telescopes this big, but they didn't work. So making it work is a really important thing. The mount is very heavy and can withstand the moving weight of about 22 tons for this telescope. The way it works is there is a mirror here at the bottom that has a parabolic bowl carved in it. The light hits that mirror, goes up and hits the second mirror up at the top. That mirror is bowed out, spreads the light down here to a third mirror, which sends the light out here, which is where you would put an eyepiece and look through the telescope, or put a camera and do observations, imaging observations. That will be done tonight and was done last night. A particular kind of imaging called spectral imaging that a bunch of high school students are working on. It is fairly advanced work for them. So no other telescope like this existed in the world. It floats in mercury. This is a sealed tub with a few gallons of mercury in it, and the telescope is literally floating in the mercury. And so the mechanical barrier only has to cover 5% of the weight. The top end of the telescope can be removed with a crane and a plate, so it can change the secondary mirror. If you don't want the light to come here, you can send it out to the side, up on top. That's called a Newtonian focus. This is called the Cassegrain focus. And if you wanted to, you could send the light down there, which is called a Coudet focus, which would be excellent for very high dispersion spectroscopy. Which means, remember the picture I showed you on the billboard outside the 150-foot towers about solar spectrum is about this big. But when you look in the SNO solar telescope and looked at the solar spectrum, you only saw a small part of it because it's spread out much bigger. Well, with this, we can spread out the spectrum zillions of feet, make it huge. And so the spacing now is a very small number of wavelengths. And you want that when you want to tell us precisely what element you're looking at, what are you doing in detail. So this was the world's largest telescope, the world's largest spectroscope, and remained so from 1908 until 1917 when the 100-inch telescope went into operation. So the biggest claim to fame for this telescope is some discovery of the Milky Way galaxy. And you might think, wait a minute, the Milky Way is a naked eye object. Go out to any dark sky. How many of you have been out to the desert on a nice dark night and looked up at the sky while you were there? You might have noticed a white band of stars across the sky. And if you haven't done that yet, why not? Tell your parents you need to go out where it's dark now and go out there and look at the sky. So this white trail of stars across the sky is called the Milky Way, which is a direct English translation of the Roman Latin Via Lactea, which is a direct translation of the Greek that I won't try to pronounce. It's Milky Way is like a road. In Armenian, it's called the Straw Thieves Highway. The Armenians are the only ones who use the word thief, I don't know why. In Oriental, Chinese, Japanese mythology, it's a river, the Silver River they call it. But we call it the Milky Way. We are inside our own galaxy. We can see it. People have been looking at that since before they were people, for thousands of years, tens of thousands, hundreds of thousands, how do I know? But they did not know what they were looking at. But eventually a guy named Harlow Shapley came along, he arrived here in 1914, and began using this telescope to study that stream of stars. And he made the discovery that, and this is my high-tech model of the Milky Way galaxy. You can build one yourself. It's so incredibly complicated, you may need some help, but this thing is the disk of the galaxy. The Milky Way is a disk with spiral arms. They're kind of painted on this thing. It's a pretty crude approximation of what the Milky Way looks like. But it's important because it's broad and flat and has spiral arms, and it has a bulge in the middle. Not quite to scale, but that's all right. This bulge on my model is a little bit bigger than the real bulge. And then these red things around it are called globular clusters. They are large clusters of stars, a few 100,000 stars, that form kind of a halo around the galaxy. This is what the Milky Way galaxy looks like. We now know that. But we did not know that in 1914. So there are two tricks that Harlow Shapley used to discover our place in the galaxy. The first trick he used is a trick we're going to use right now because I want all the students to get up and crowd around me here. Just stand around me. Oh boy, that's right. So, if you look around that way and then look that way, do you notice any remarkable difference in how the students around you are spread out? You do. It's pretty much the same, isn't it? It's pretty much the same. Now it's your turn. You look that way, and what do you see? How many people? A lot? A few? One? Two? Not a lot, but okay, there's people. Now turn around and look at it. How many people do you see? One, two, three, okay. So is there more than three that way? So if I asked you, are you in the middle of the group of people, what would you say? Hang on a minute. If you were in the middle, what would you expect to see? That's right, you would expect to see equal. Do you see equal? So are you in the middle? No, okay, Because you see pretty much the same this way as you see that. You must be in the middle. She sees a whole bunch of people that way, you see that. So she must not be in the middle. So if you look up at the sky and you see a whole bunch of stuff, and you say, it's all red, and then you have over there.